Hello everybody, so in this video we're going to look at another type of conic section, which is an ellipse. An ellipse is formed by the intersection of a cone with a plane that cuts through only the curved surface of the cone, and it has the general Cartesian equation of x squared over a squared plus y squared over b squared, where a and b are both constants. And it has the parametric equation where x is a cos theta and y is b sine theta. And we can see how these parametric equations work. If we were to substitute a cos theta into x, well, we get a cos theta all squared over b a squared plus b sine theta substituted into y, so b sine theta all squared over the constant b squared, and this will equal 1. We can square this out and we get a squared cos squared theta over a squared plus b squared sine squared theta over b squared. This equals 1. We can see the a squareds will cancel and the b squareds will cancel, and we know the trigonometric identity where cos squared theta plus sine squared theta equals 1. So hopefully that gives you an idea of how these parametric equations work. Okay, so in example 1, we're going to sketch each of these ellipses and we're going to find their parametric equations. So for equation A, we're going to sketch x squared over 16 plus y squared over 9 equals 1. So to find the point on the y-axis, we'll say when x equals 0, well, a squared over 16 would be 0, so we're left with y squared over 9 equals 1. We can move the 9 to the right hand side, so y squared will equal 9. So therefore, y will equal plus or minus 3, which we can plot here as positive 3 and here as negative 3. And when y is 0, we'll find the points along the x-axis. So y will be 0, so this means y squared over 9 will be 0, so a squared over 16 will equal 1. So x squared will equal 16. So therefore, x will equal plus or minus 4. And we can plot these on our x-axis at positive 4 and negative 4. So our ellipse will look like this. And for our parametric equation, we can see that a squared is 16, so our a value will be equal to 4. So if we have a point here, point P, we can say we've got 4 cos theta. Our y value will come from this b squared, which is 9, so b will be equal to 3. So we'll have 3 sine theta. Okay. And for question B, we can see that a is 5, and this a has positive 5 and negative 5. So we can say this will be positive 5 and this will be negative 5. And the b value will be 3. So our y coordinates will be positive 3 and negative 3. And for our Cartesian form, we'll have x squared over a squared, well, 5 squared is 25, plus y squared over b squared, and b is 3, so over 9, and this will equal 1. So I hope this has given you an idea on how we can sketch each of these ellipses and find their parametric and Cartesian equations. Okay, so let's move on to question 2. So in example 2, we've been asked to show that the equation of a tangent to the ellipse, given here the Cartesian equation, at point P, where x and y are defined parametrically, is AB equals xb cos theta plus ya sine theta. So the first thing we need to do is we need to find the gradient function, which is dy by dx. Now we could differentiate this implicitly, or we can differentiate these parametrically using a chain rule. I think it's much easier to use the chain rule with the parametric equations. So to differentiate parametrically using the chain rule, we know that dy by dx is equal to dy by d theta multiplied by d theta by dx. Because what will happen is that these d thetas will cancel and we're left with dy by dx. So to work out dy by d theta, well, we know that y is equal to b sine theta. So therefore dy by d theta will be b cos theta. And we know that x is equal to a cos theta. So therefore dx by d theta will be minus a sine theta. And by flipping this upside down, negative 1 over a sine theta. And when we multiply dy by d theta by dx, we get dy by dx will be minus b cos theta over a sine theta. Okay? And now we can use this gradient function to find the equation of a tangent. We've just worked out our gradient. We've got the general form of x1, which is a cos theta, and the general form of y1, which is b sine theta. So substituting these in, we get m minus b cos theta over a sine theta multiplied by x minus x1, which is a cos theta, is equal to y minus y1, b sine theta. We'll move the a sine theta to the right hand side and we'll expand out these brackets. So we get minus bx cos theta plus ab cos squared theta is equal to ay sine theta minus ab sine squared theta. We've been asked to leave the ab on the left hand side, so I'll move this negative ab sine squared over to here, and I'll move the negative bx cos theta to the right hand side. So now we get ab cos squared theta plus ab sine squared theta is equal to bx cos theta plus ay sine theta. We can factor out the ab, and then we're left with cos squared plus sine squared. But cos squared plus sine squared is 1. So we have ab is equal to bx cos theta plus ay sine theta. And this is the general form of a tangent to an ellipse. Okay? And in question 3, we're going to look at finding the normal to an ellipse. Okay, so in question 3, we've been asked to find the equation of a normal to the ellipse a squared over 16 plus y squared equals 1 at the point P, negative 2 root 3 and a half. Now we worked out from question 2 that the general gradient of a tangent is minus b cos theta over a sine theta. So we can use this to work out the gradient of a normal. So the gradient of a normal will be the negative of the tangent. So we'll cancel out this negative here and we'll work out the reciprocal of this fraction. So we'll move the a sine theta to the top and the b cos theta to the denominator. And this will be the general gradient of a normal. And we can see from this equation that a squared is 16, so a will be 4, and b squared is 1, so b will be 1. Now we can work out theta using this value of a and the parametric equation for the x. And we're told that the x value is negative 2 root 3. So negative 2 root 3 will equal a cos theta. So theta will be the arc cos of negative 2 root 3 over 4. And this gives us theta is equal to 150 degrees. But if we consider the range between 0 to 360, we know that there'll be another solution when theta equals 210 degrees. And we can work out which of these to use by considering the y values. And at point P, we're told that y is a half, so 1/2 will equal b sine theta. So in this case, theta will be the arc sine of a half, so theta will be 30 or 150 degrees. And in this case, we need to choose theta which works at both the x and y values. So in this case, theta is going to be 150. Okay, so now we have theta is 150, we can put this angle, theta, into the gradient of normal along with our a and b values. So the gradient of a normal will be dy by dx, will be a sine theta, so 4 sine 150, over b cos theta, so the cos of 150. When we work this out on our calculators, we get negative 4 over root 3. So this is the gradient of a normal. So we can work out the equation of a normal using the gradient, negative 4 over root 3, lots of x minus x1, so minus negative 2 root 3, so plus 2 root 3 will equal y minus y1, so minus a half. We can move this root 3 to the right hand side and multiply out the negative 4. So we get negative 4x minus 8 root 3 will equal root 3y minus root 3 over 2. And now we'll multiply out the 2 to cancel out this division. So we get negative 8x minus 16 root 3 will equal 2 root 3y minus root 3. And then we'll move all the terms from the left hand side to the right hand side to make this positive. So we get 0 will equal 8x plus 2 root 3y plus 15 root 3. Okay? So I hope this has given you an idea on how to sketch ellipses and how to find the equation of a normal and tangent to an ellipse. So if you did find this helpful, please like and subscribe, and you can download the full lesson and worksheet from my website mrmathematics.com. Thanks for watching and take care.